Hello, I'm Jason Kendall, and I'd like to welcome you to my introductory cosmology channel. I've been going through Dr. Barbara Ryden's textbook, Introduction to Cosmology, and now I'm up to Chapter 3, Section 5, the Friedmann-Lemaitre-Robertson-Walker metric, or How We Measure Cosmological Spacetime. Before I begin, I just want to say thank you to my Patreon supporters and my YouTube subscribers. Their support means a lot to me because it does keep this channel going. If you like what's been happening on the channel so far, please join us because I give all my supporters and members special perks and advanced views to all my videos. Now let's get back to it. Last time we looked at the spatial metric for an isotropic homogeneous space with constant and uniform curvature. We ended on these particular coordinates, called hyperspherical coordinates, because they're what Ryden uses in her textbook. They describe an embedding of a three-dimensional space in a four-dimensional space. These equations represent what's called a three-surface of a four-ball. That is to say, it's a three-dimensional surface with some constant curvature embedded in a flat four-dimensional hyperspace. Let's now go over how the curvature constant k relates to the radius of curvature for the space. We see that in the flat case that k equals 0, meaning no curvature. The positively curved space, k equals r squared, and likewise for the negatively curved space, k equals minus r squared. In both of these cases, the big R is the characteristic constant curvature radius for the space. What's interesting about these coordinates is that for the ease of pedagogy and understanding, it's usually broken up into those three separate functions. However, these three functions are exactly the same as the analytic single function you see off to the right. In that nerfy-looking function, k has some fixed value, and little r is the independent variable as the radius for some central origin point. The radius of curvature, r squared, is actually the inverse of k. We'll see how that gets involved later. As for the analytic function, if you put in the positive value for k, then you get a sine function. A negative value for k gives the hyperbolic sine function, and k equals 0 wipes out every term in the summation except where n equals 0, which gives the simple middle result. Either with the analytic function or the broken out trio, this spatial metric satisfies a lot of things we need. It's uniformly curved and isotropic around every point in the space, as well as homogeneous throughout the space. We saw this in an earlier video too. Let's now begin the process of connecting these geometric considerations into a relativistic theory of gravity. Our first step to connecting to such a theory is to go back to our special relativistic theory, the one without gravity. In my previous video on special relativity, which if you haven't seen, you'll want to go back and watch that, then come back here, I showed that the Minkowski spacetime metric was our solution to a spacetime that is homogeneous at every point in the spacetime and is isotropic around every point in the spacetime. Now that I've looked at curved spaces, we see quite readily that the spatial part of the metric is this exactly flat isotropic homogeneous space from the previous slide. A really important side point is that ds squared is what's called the spacetime interval, which is invariant under changes of coordinates. The coordinate changes can be translations, rotations, or boosts. No matter what, it is this spacetime interval that shows the true distance between two events in space and time. Space and time are so intertwined as both theoretical and experimental entities that we cannot reasonably separate them any longer. That's why we always say spacetime rather than space and time. But what's a good intuitive motivation for this metric? The Minkowski spacetime metric is the one we use when we wish to understand the propagation of light due to Maxwell's equations. The factor c was a speed that showed up in those equations. It served to tell us the wave propagation speed and is constant no matter the relative motion of the observer or the emitter. This led Einstein to discard Newtonian kinematics and extend Galilean relativity's reach into a relative time measurement. So let's use this metric and ask, how does a photon travel from there to here in this spacetime? We can assume, without losing any generality, that our photon travels to us from some distant galaxy positioned at coordinates r, theta, and phi. It travels in some straight line from there to here at r, theta, phi equal to 0. This is the situation in the Stickman cartoon off to the left. Next, since we're traveling in a straight line, there is no change in d theta or d phi, which means that d omega is then just set to be 0. We also know that photons propagate at the speed of light. In terms of our coordinates, we will require that the rate of change of the radial coordinate with respect to time must be equal to c, the speed of light. The only value of the spacetime interval ds that satisfies this condition is for it to be exactly 0. Therefore, the path of a photon is called a null spacetime interval. According to light, it does not travel any spacetime distance at all. To us, it may have started off as an energy packet keeping an electron in a higher orbital level than the ground state until it's released by the electron. It then travels through space until it hits, say, another atom of the same type and excites that electron into that higher state. That's what we would see from the outside. We might say that the photon traveled 8 light years from a distant star to our detector. But to the photon, it never left the atom. One atom is exactly the same as the other to it, and no spacetime interval is traversed between them. Another way to think about it is photons don't experience time or distance because these two things are exactly the same to them. In addition to this conundrum, anything that travels at the speed of light travels on a null space-time geodesic. This includes gravitational waves and possibly theoretical zero-mass neutrinos. The key is that the photon has no mass, and nothing that has mass can travel at the speed of light or accelerate up to it. Anyway, we'll need this in later lectures on photon propagation in the spacetime that incorporates the effects of gravity. It is this definition of the metric, 4 dimensions with 3 space-like dimensions and 1 time-like dimension, that has the specific sign signature of minus plus plus plus, as can be easily seen in the topmost version of this metric. That puts us into what's called a pseudo-Riemannian manifold, and not a Riemannian manifold. If it were plus 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 plus, it would be a Riemannian manifold. This extra change in signature makes it a pseudo-Riemannian manifold. It is this minus plus 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 signature that permeates all relativistic theories of gravity, whether Einsteinian or otherwise. Next, we do know that there's gravity in the universe. So how does that change the Minkowski flat spacetime metric? To see what that means, we need to ask if there are any additional symmetries, both spatially and temporally, that allow for the change of the metric through time. The answer is the Friedmann-Lemaitre-Robertson-Walker metric. It is what we get when we say, what if the space were not just uniformly flat, but rather could be uniformly curved? We already saw how that symmetry plays out. In addition, we've added a time-dependent scale factor to the spatial part of the metric that affects all spatial dimensions uniformly and equally across the entire spacetime. This metric is the one that is used in standard cosmological studies. It is the fundamental baseline idea that permeates all measurements in the field. We see it here in 2 forms. Across the top, we see it in the spacetime interval form, which adds up all the contributions and tells us the total spacetime distance interval. On the bottom, the matrix form shows the metric in its tensorial form, g mu nu. There are 16 possible elements to the metric, but the symmetry of the space eliminates 6 of them, and the symmetry with respect to time eliminates 6 more. The zeroed-out space-space components of the metric show that the rotational and translational spatial symmetry is complete and uniform across the entire spacetime. The zeroed-out time-space elements show that the passage of time does not affect the measurement of space. It also says that changing locations in space does not affect the rate of change of the passage of time. Time flows at the same rate at all locations in the space. It also has flowed at the same rate for all of cosmic history for all locations in the metric. This is an incredibly large symmetry for the temporal aspect of time. Let's now go over each part of the metric in turn. First, we note that the signature stays with the pseudo-Riemannian signature minus plus plus plus, as can be quickly seen. Next, we've allowed the flat spacetime to also have a uniform curvature, which is encapsulated in the denominator for the dr squared component. This brings in our spatial metric from before, and just to make things deliberately confusing, I've converted back to using the reduced circumference coordinates for the spatial metric. It's quite a bit easier than carrying around the s sub kr function thingy, and since we've learned previously that a change in coordinates doesn't change the metric, this version describes the same space, but with a different definition for the radial component. We can just go back and forth between the coordinate choices, using the one that makes our current job easier. Again, we maintain spatial homogeneity and isotropy around every point in the spatial portion, and we allow the spatial part to now have a globally uniform curvature. This extension of the Minkowski metric is really not a big deal. The Minkowski metric is just a special case, and if the curvature is large enough and we choose a small enough region in that space, it's really hard to tell if the space has curved at all. This means that for a large curvature, we can always find a small spot that is locally flat, which will be very important later. It's also important to note that this spatial metric portion is called maximally symmetric. This means that every point is equally special in this space, or if you will, there are no special points in the entire space. Next, we look at the scale factor a of t. It is only a function of time. It essentially says that the space that underpins every ruler or measuring stick grows at the same rate as all the others in the entire space. The scale factor is the way to expand or contract space across history as some function of time. From a Riemannian manifold perspective, this merely means that our definition of length is variable, and the concept of length itself begins to look more like an angular measurement, which is unitless. In this particular formation of the metric, however, the metric scale factor is some unitless number, and r still carries units of length. Wherever the units live in this equation, the scale factor affects all points in the maximally symmetric spatial metric equally. Little r is a real distance that increases by some factor as time passes. It could decrease, or it could do some wibbly-wobbly, timey-wimey thing. Importantly, because of the maximal symmetry of the spatial portion of the metric, the scale factor is not a function of location or orientation. It is an integral part of the configuration of the homogeneous and isotropic space, and that makes it completely independent of the position in the space. On the lower right, I've given a couple of hints as to how it appears in the standard FLRW cosmology. On the top is the evolution of the scale factor as a function of time for the standard lambda CDM cosmology. Dot A is the first time derivative of the scale factor. All the omegas are just numbers that give the current cosmological densities compared to flat space of cold dark matter, baryonic matter, radiation, curvature, and dark energy. All the omegas are observable, as is the Hubble constant h sub naught. Once you know these observables, then you know the scale factor's full evolutionary history and its future. In practical terms, it is typically very hard to get these omegas, so the next easiest thing is to say, I have no idea how it evolves, but I can try to get some values out of some distance using an approximation. And that's what the last equation on the right is all about. It's a Taylor expansion of A as a function of time. Here, we don't assume that we have any idea what the actual functional relationship that the scale factor has with time. We just try to find some distant objects that give us a recession velocity at various cosmically large distances. If the recession speed varies with distance and isn't a strict linear Hubble law throughout the universe, then we'll get a first approximation for the acceleration or deceleration of the universe according to the scale factor. To let the cat out of the bag, it was the study of this last equation and its observational consequences that led to the discovery of dark energy. Lastly, the scale factor only affects the expansion of space. It does not affect people or planets or galaxies. So the cartoon across the bottom says that we can watch the universe expand around us. Our stickman is not moving anywhere, but he's moving forward in time. As the time advances for an unmoving galaxy, the distance between stickman and the far galaxy grows by the scale factor. So what exactly is this time here? Back in our special relativity studies, we learned that time measurements can be different due to the relative motion of the observer and the emitter of a signal. This is also true of spatial measurements. I went further and charted out the extensive experimental evidence for the relativity of both space and time. But here, we have a time that appears to be outside of all that stuff going on. And we're going to call it the cosmic time. This haughty name seems to imply there's a single clock governing all spacetime, but that's not the case. Our time component is the time that is measured by an observer at the center or origin of the coordinate system. It may sound dodgy to allow space to be uniform, isotropic, and homogeneous, but the time is only valid for an observer at the center of these coordinates. However, if you take a step back and notice that this cosmic time would be what's measured at any observer at any point in the cosmos. Boy, that still sounds kind of dodgy, but the time cannot be simultaneously measured anywhere except at the observer's location. All times farther away are necessarily measured as being some time ago. This formulation of cosmic time implies that we look back in time the further in the distance we look. This means that the cosmic time is homogeneous for all observers in the universe because the behavior of this metric will be the same at all locations. Also, the cosmic time is isotropic. As we look back in time, the farther out in space we look, the farther back in time we look. And this look-back time is 100% the same in all directions. If it were not isotropic, then we would measure time passing faster in one direction than another. This would mean that the oldest galaxies would be different in one direction than another, and that's not what we measure. We measure all directions as having the same age for a given radial distance. Therefore, we can be happy with our definition of cosmic time. It's just what we measure to be right here. Look-back time, then, is relative to our clock right here. What we can say about some clock way over there measuring the cosmic time on some planet in a galaxy 100 megaparsecs away is that they'll measure us to be in the past relative to them. We've therefore tied the cosmic time to light traveling along null geodesics. We can then derive meaning from look-back time by surmising what a distant galaxy might look like today due to known physics. So unlike the special relativistic flat, unchanging space, our allowance of an expanding spatial metric gives rise to this use of cosmic time. Our current choice for cosmic time being the time measured by the observer at the center of the coordinate system can be more accurately stated as the time measured by a fundamental observer surrounded by objects in a co-moving coordinate system that is being carried by the expansion described by the scale factor. But what does that mean? To answer that, we need to go back to our scale factor cartoon. Let's say we somehow know that the distant galaxy is not moving at all locally. It's at rest at its home. This would be possible if it were an isolated field galaxy far from any clusters. Let's say it's in the gravitational balance point between a bunch of galaxy clusters. Then, in this case, our theta phi coordinates would not change at all as the time passes. But the distance between Stickman and far galaxy would still grow. We call these coordinates co-moving coordinates. It means that these coordinates are merely tick marks on a ruler, but not their physical size. The scale factor determines their physical dimensions. To see the difference, let's pretend you've been handed, by some guy, a thing called a stick. On this stick, we're told to mark 10 large, equally spaced tick marks. We are then asked to mark 10 smaller tick marks between each of those big tick marks. We then do it again between those. So now we've got 1,000 equally spaced ticks on a stick. Well, that's great, says the guy who handed you the stick. Well done. But this guy's a bit of a jerk, and he doesn't tell us about the stick. He then takes both ends of the stick and pulls on them. The stick expands, spreading out all the ticks on the stick equally. How long is the stick? The stick went from being maybe a meter long, and now it's 10 meters long. It was scaled up by a factor of 10 in the time it took the guy to pull on both ends of the stick. Notably, all the ticks still have the same relative relationship with respect to each other. The physical size of all the lengths on the stick has gone up by a factor of 10, but the tick locations themselves relative to each other did not change. That's the sense of co-moving coordinates. They are the tick marks on the rulers that permeate the universe. They don't have physical dimensions in of themselves, but the scale factor of the expansion bestows that physical length upon them. That's why I started the story calling it a stick rather than a meter stick. Why? Our story does some conceptual damage because the story says that the expansion happens to an object in a space that itself doesn't experience the expansion. But co-moving coordinates in an expanding universe do not indicate that there's a space into which they are expanding, just like a manifold having a constant curvature, which is an inherent property of the space itself and does not rely on an embedded physical extra dimension. This expansion is the same thing. How might you ask? The best analogy that I can think of is this. Take the integers, the counting numbers. These can be your ticks on a stick. Now double every number. Now you're counting by twos. but the distance between two numbers has jumped by a factor of 2. But you still have exactly the same number of ticks on a stick as before, and the actual size of the infinite set of integers has not changed at all. And we haven't expanded the integers into, say, the real numbers. They're still the integers. This analogy is pretty loose, but it gets at the idea that the size of the distance between the integers is not actually a property of the integers. We don't need more integers in order to keep an infinite set of integers that are twice as large. It's just a property of the cardinality of the integers. The takeaway here is that co-moving coordinates do not change as the universe expands unless the distant objects have their own proper space motions. We know that the universe has whole different kinds of things in it that are really not homogeneous or isotropic. From planetary size scales all the way up to galactic size scales, we can easily note clumpy things that look really different in different directions. So it begs the question, on what size scale does the Friedmann-Lemaitre-Robertson-Walker metric apply? Another way of asking the same question is to say, at what size scales do all other forces concede to the strength of the expansion of spacetime? Planets, people, and small things are held together by electromagnetic and gravitational forces that are far stronger than spacetime expansion's effect. Large objects are bound together by gravity, and by large, we mean galaxies and on up to the size scales of superclusters of galaxies. Things about 200 megaparsecs in size are the largest possible gravitationally bound structures. When talking about cosmology, we have a sample size box of about roughly 10 billion light years on a side. We find that in such boxes, no matter where they're centered on, whether they're centered on a galaxy cluster or a cosmic void, the average density of each of these boxes is nearly identical. The average density is about 1 proton's worth of total energy per cubic meter of space. And this is not what we see locally, where you can have differences in densities from cold interstellar space down to the core of a neutron star, and these can differ by a factor of 10 to the 30th. On the largest cosmic size scales that I just described, the density differences are on the order of less than 1 part in 10,000. As you can see, the largest cosmic size scales are far smoother than the lumpy things of planetary and stellar size scales. We have two main ways of measuring the amount of homogeneity in the universe on these large size scales. We can measure how galaxies are distributed across space on scales between, say, a few megaparsecs up to hundreds of megaparsecs, and then we can construct a mass density map of the universe, not just nearby, but at all points throughout cosmic history, because the farther away we look, the farther we look back in time. Second, we can measure the cosmic microwave background, which is the remnant light from the Big Bang, and map the inhomogeneities imprinted on it. The temperature fluctuations observed in this mapping show us the matter distribution of the cosmos. I'll talk about both of these in great detail in later lectures. ESA's Planck mission found that the average density fluctuation in the early universe was roughly the same on all cosmic size scales, about 1 part in 30,000. To support this, the galaxy distribution observations found a value that's entirely consistent with these CMB measurements. The resultant galaxy structure evolution models and simulations are in total agreement with the CMB and theoretical predictions. We can therefore be really confident in the metric which describes a universe that's roughly homogeneous and isotropic everywhere, with only small, quantifiable imperfections superimposed on top of this uniform background. The smooth beginning that occurred as part of the inflationary epoch was then littered with this clumpy and clustery universe we see today. But even with all this, it is sufficiently uniform on cosmological size scales to justify using a metric that assumes perfect homogeneity and isotropy. We need to do a much deeper analysis of the FLRW metric in order to understand its connection to gravity. Since gravity is a dynamic process that causes things to move, and since you've probably heard the phrase, matter tells gravity how to curve and curvature tells matter how to move, we should expect that a spacetime's effect on mass and energy should be something like a slope down a hill. In practical terms, this means a rate of change with respect to spatial or temporal variables. What this looks like mathematically are the first and second derivatives of the spacetime metric. For the ease of our calculations, so we don't carry around a bunch of stuff, I'm going to do the standard cosmological convention of setting c equal to 1. This is because c, being a speed, is actually a conversion factor between meters and seconds. When you geometrize the world, you try to put everything in terms of length. I went over this process when I discussed Planck units way back in my Chapter 1 video. Here, we're not worried about the highfalutin philosophy, we just don't care to write c everywhere. And since it's legal, we'll just do that. Also, I'm going to do this whole exercise starting with the reduced circumference coordinates of the FLRW metric. They look prettier than the hyperspherical coordinates in my opinion, and are commonly used in the literature. Later, I'll go back and contrast the result with the hyperspherical coordinates to show that the spacetime really is the same no matter what coordinates you use for the metric. But for now, we want to develop the process with this form. First, I put the metric into what I did with the matrix, with the g sub whatever. These are just the tensorial labels for each element in the spacetime interval equation. I then raised the indices of the metric's components. That's the group off to the right. To raise both, the end result is to make the inverse of the component. The metric times its inverse is the identity matrix, which means that each component times its inverse is just 1. You can see that all the exponents in the raised version now have a minus sign. We'll need these raised index g's later. Across the bottom are all the non-zero first derivatives of each of the components. I'm using a common shorthand notation for the derivative, the comma notation. Remember that all of these are rates of change with respect to some other coordinate in the metric. All the spatial metric components have a time derivative and a radial derivative, but only one has an angular derivative concerning theta. Typically, we might call first derivatives slopes or gradients. However, in a non-Euclidean spacetime, we need more elements to get that gradient. These are only partial derivatives and not the whole story. To describe the connection between the metric and gravity, we have a lot of mathematical juggling to do. First, we need to calculate what are called the Christoffel symbols associated with this metric. We saw these before when we looked at the parallel transport and traveling along geodesics. These symbols, defined by the green equation across the top, connect the metric to the shape of the manifold itself. What they describe is basically how a vector changes from one point to another in a spacetime. You do need something in your mathematics to account for the fact that your coordinate system changes along the way, in addition to any changes that may occur to the actual vector itself. The partial derivatives from the previous slide don't do this. Such derivatives always assume that the basis doesn't change, but in a curved space, the basis vectors do change. And then, to account for this, we're going to replace the ordinary partial derivative with what's called the covariant derivative. The part of the covariant derivative that keeps track of the changes arising from the change in coordinates is this Christoffel symbol. They encode how much the basis vectors of the coordinate system change as we move along in the direction of the basis vectors themselves. This changing derivative as we move through the spacetime is exactly what we expect from a curved spacetime. We know that the values of the metric change as we putter around the spacetime, so that means compared to where you are now, a nearby location in curved space rotates, translates, and boosts a vector you place over there. What we see across the top are all the elements that go into calculating the wad of Christoffel symbols you see across the bottom. We see that the symbols rely on the partial derivatives from the previous slide and the raised index metric. If you look carefully, for a given value of m, I, and j, we need to sum over the index L. Fortunately, because of the symmetry of the metric, these are pretty easy to calculate. It's not really critical to go over all of them, but you should notice that there are a lot of symbols that are equal. There are also a lot of them where the symmetry of the spacetime has made the symbols symmetric in the I and j lower indices. Next, time derivatives of the scale factor only appear in the symbols where t is one of the indices, and the curvature constant k only appears in 4 symbols, where the GRR component of the metric raises its head. Now let's put these symbols to work. We'll work them using the Riemann curvature tensor. In a much earlier lecture, I described the process of how we can determine curvature by parallel transporting a vector around a short loop following geodesics. If the space is curved, then the vector's final orientation and possible magnitude will deviate. The curvature tensor, which you can think of as a powerful function, takes as inputs the coordinate basis for the space, some vector you want to push around the space, and the lengths of the sides of the loop, and spits out a little vector that is a measure of the space's curvature. In this diagram, the starting vector is yellow v with an arrow over it down in the lower right. That's the red arrow pointing straight to the right above it. We then parallel transport yellow v counterclockwise around the loop back to its original location. This loop finishes with the orange arrow. The orange arrow differs from the original red arrow by some delta v, which is seen in the little green arrow. The Riemann curvature tensor is the object that tells us how much and in what direction little green delta v is pointed. We saw that the Christoffel symbols are composed of first derivatives of the metric and show that these are a gradient along a geodesic. The curvature tensor is composed of either derivatives of the Christoffel symbols or a product of two Christoffel symbols, and this works out to be second derivatives of the metric overall. To connect it to gravity, we next need the Ricci curvature tensor. We see that it looks a lot like the Riemann tensor, but we're summing up over the first and third indices. To indicate this, I've changed rho and mu to a, and I've also changed the index nu to I and sigma to j. The Ricci tensor is important for the upcoming work, so let's calculate some of its values for our metric. Our first component we'll calculate is the time-time component of the Ricci tensor. I've pulled all the Christoffel symbols along to view, but it's really the four parts of the tensor I want to show you. The first two parts are partial derivatives. The red one across the top is 0. Using the Einstein summation convention, there are 4 things to add up to make up the red equation, but each relies on a Christoffel symbol with TT as a lower index. All 4 possibilities are 0, so their sum is 0. The next one, in orange, we do have to worry about. There are 3 non-zero symbols which all happen to be equal. When we take the partial derivative with respect to time, we get 2 terms that only depend on the scale factor and its time derivatives. Double dot means 2 time derivatives, and single dot means 1. For those with a very keen eye, this kind of looks like an acceleration and a velocity squared, which are related to energies, and that's good because gravity chats about potential and kinetic energy. But it's far too early to start in with that yet. We've only just started. The third equation in blue is 0 for the same reason the red one is, and the fourth equation in purple adds up 3 identical terms with the first being 0. To get the Ricci tensor for the time-time component, we add all these up. Happily, 2 of the terms cancel, leaving a rather simple result which we'll pull together in a moment. The RR component of the Ricci tensor is a real mess. There are a large number of terms and only a few of which are 0. Again, the top 2 are the first 2 terms in the Ricci tensor summation, which each themselves are sums over partial derivatives. The bottom 2 are also sums of products of Christoffel symbols. The RR component has a lot of curvature constant k terms, a few scale factor terms, but no presence of theta or phi coordinates anywhere. The radial symmetry, meaning the isotropy of the space, is apparent with that. When we add everything up, we get a lot of canceled terms. This makes the final result of the RR component of the Ricci tensor really a simple-looking thing across the bottom. Now, just for the sake of brevity and the fact that I went a little crazy with all this, I'm going to skip over showing you the nitty-gritty of the theta-theta and phi-phi components of the Ricci tensor. If you wish, you can pause the video and try doing the algebra for yourself. I did for this video, so it's not impossible. It's just a bit tedious. Perhaps someone in the comments will point to a Mathematica script that would create and solve these. That'd be fun to see. So I've collected all the components of the Ricci tensor on the left. The top 2, I showed the derivation, and the bottom 2, the r theta theta and r phi phi, I didn't. What's apparent from all of them is that the spatial components all have a factor of an a double dot a plus 2a dot squared plus 2k. This is multiplied by the corresponding spatial metric GRR or g theta theta or g phi phi. We just need to divide out the a squared to get the Ricci tensor for each one. All 3 space-based components for the Ricci tensor can be summarized on the right, r sub ii. G sub ii is one of the spatial metric components. The time-time component of the Ricci tensor sits all alone at the top. Our next object that we now need to construct is the Ricci scalar, r. To do so, we need the raised index versions of the metric, and we need to contract the Ricci scalar by summing over all the alphas and betas you see there. Right now, I really want to emphasize that this Ricci scalar r is exactly not the same as the radius of curvature in the metric. It is just an extremely unfortunate turn of events that Riemann and Ricci both begin with r, and r is often used to show a radius for spheres and circles and such. Please don't worry about it, it'll be fine. If we sum up the products of the metric and the Ricci tensor for all four combinations, we get the expression in yellow at the bottom for the Ricci scalar. It's now interesting to note that we've just hemmed in the units for the curvature constant k. The scale factor a might be unitless or have units of length, depending on your metric's definition. No matter what they are, they would cancel out. But there are two time derivatives in there. To match the units, k must have units of inverse time squared. But remember at the beginning we set c equal to 1? That means we should geometrize it and call it inverse length squared. The curvature constant has units of something per area. What that something is might not end up mattering. What is important is that the k contains the nature and size of the curvature in whatever isotropic, homogeneous, and uniform spacetime we choose. Okay, let's file the Ricci tensor and scalar away for a moment to address a needed clarification from the textbook. Dr. Ryden uses a mostly non-standard coordinate configuration for her version of the Friedmann-Lemaitre-Robertson-Walker metric. She uses throughout the text an altered version of the standard hyperspherical coordinates. The good thing about using either form you see here is that the radial component is almost a distance. It's a co-moving coordinate distance specifically, but it's much more like a distance from the origin than the reduced circumference coordinates, which is actually not based fundamentally on a distance from a central point in the coordinate system. The upshot is that dr is very much like a little change in the co-moving radial direction than the previous metric. Since Ryden will show us a lot of things that relate to distance very soon, this particular coordinate choice makes the results we'll get easier to read and interpret. On the bottom is the real and true version of the standard hyperspherical coordinates where the curvature constant k is a real valued number that can be positive or negative. It incorporates both the size and nature of the constant uniform curvature, one number to rule them all, and so forth. But Ryden takes a different turn. She implicitly uses the gnarly analytic function that we saw before and fishes out the two parts of the curvature constant k, the size and the sign. She labels the three types of universe, closed, flat, and open, as kappa being +1, 0, or -1. This is pretty nice because it follows our intuition about the three different types of uniform curvature. It also helps in a later argument about how one type of universe cannot become another. We'll talk more about that in our toy universes chapters later. Ryden also pulls out the radius of curvature into r sub 0, making it into a ratio with the co-moving radial coordinate. This looks neat and helps to remind us that there's no units on an argument for a sine or a hyperbolic sine function. With the curvature scale size, r sub 0, out in front, we can kind of intuit an amplification of the radial curvature from the functions. On the top, the positively curved space curves back onto itself at a co-moving distance r0. The open universe's negative curvature leads to an exponential growth on the scale of the co-moving radial coordinate. The kappas serve to restrict our thinking to one of the three choices. The link between the two equivalent flavors of this metric is shown on the right. The curvature constant k is just kappa over r0 squared. This is obvious by comparing the two triplets. Using this form of the metric, we're going to repeat what we did before. Just to not drive myself bonkers, I've flopped back over to using the s sub k form of the hyperspherical coordinates rather than the s sub kappa. It works out to be exactly the same thing in the end. First, we note the metric itself across the top. We're going to follow Ryden's example and leave in all the constants like c, g, the Boltzmann constant, and the Planck constant. This is an introductory course, so there's really no reason to add the confusion by using the elegant Planck unit abstraction. We can always set them to 1 to make it elegant later. With that, we see the metric's tensorial components over on the left. As expected, there are 4 of them, with no cross-product terms, and then we take the partial derivatives of each of these metric components with respect to each of the coordinates and keep only the non-zero results. We've now got something that kind of starts to look nasty there, a partial derivative with respect to radial coordinates of the s sub k function. That's going to give us a wallop of a headache in just a moment. One big change is that we do not see the curvature constant k anywhere except as a naughty little subscript. It's buried inside that s sub k function. Right now, we don't want to evaluate the partial derivative of that thing. We'll get to it shortly. Next, we use all those partial derivatives to construct our Christoffel symbols. These look different from before, again with the addition of c for the speed of light, and the s sub k and their partials floating about. Near the bottom, in addition to the product of s sub k with its differential, we're now even seeing the ratio of the partial to the actual s sub k function. At this point, doing that algebra would make even the geekiest mathophile wheeze. We'll leave it in this form and hope the juice is worth the squeeze when we evaluate it later. Now for your edification, I wrote out all the partial derivatives for all the Christoffel symbols, rather than obfuscate and prestidigitate like I did before. This time, no dodging. This is truly ugly stuff, and there's a lot of it. We've got squares of partial k's, we've now even got second partial derivatives of s sub k, and worse, multiplied by s sub k. I really have no idea what that function would look like analytically, or even if there's a good way to express it other than what I'm doing here. Given this higgledy-piggledy conflagration of scale factors, c's, and various trigonometric thingies, it seems wild to hope that this will somehow sort itself out into a simple and rational form. For the Ricci tensors, I'm really not going to go through all the paperwork and image creation on my slides. I'll just pass that up and show you the end result. When we combine and sum all the appropriate Christoffel symbols and their derivatives, we actually do get these components below. I really do encourage you to try it out. You can use my video as a check on your progress to see if you got it right. You might as well try it. You're this far along in a proper introductory cosmology course, and if you were sitting in my class, I would make you do it as homework. So, chop chop. What's interesting about all these forms of the Ricci tensor is that it's really not far off from the other metrics component tensors at this point. We have a bunch of partial derivatives of the s sub k function and some ratios of them. Since the space is the same, and even though the coordinate choice is different, we should expect the Ricci tensor to be very much the same as before. Somehow it should work out. You can see that there are only two different terms involving s sub k to evaluate: a second partial of s sub k over s sub k, and 1 minus partial s sub k squared over s sub k squared. Let's see what they work out to be. To evaluate both terms, let's please not use the analytic function and just evaluate the equivalent triplets. Since we're back to the standard hyperspherical coordinates, I'm going to evaluate them in turn. For each of the real-valued ranges of k, we have three functions s sub k. The second line is each partial derivative, and the third line is the second partial derivative. Using the definitions of sine, cosine, and their hyperbolic equivalents, we find that all three regions of k have the same result for these two expressions from the Ricci tensor. That's some dark academic magic I implore you to replicate on your own. You'll be pleasantly pleased with yourself for winning it. Now let's plug these results back into our Ricci tensor components to see what we get. As you can see, we've nearly completely recovered what we had with the other metric. The principal differences lie in the existence of the c squared and the s sub k function prefixes, rather than the other prefixes from the previous metric. But we recovered the expression in the parentheses. That is exactly the same as before. The Ricci tensor's components are related to the metric we are using, but the s sub k replaces the r squared from before and encodes the curvature, which is now absent from the RR Ricci tensor component. That 1 minus kr squared factor got pushed into the s sub k. This is what happened by choosing a friendlier co-moving radial component for the metric. The rotational components are getting altered by the shape of the spacetime. Let's now see what the Ricci scalar shows with these components. Just like before, we can summarize all the spatial components off to the right. This is exactly the same form as we saw before. The Ricci tensor components work out to be equal to the metric component, matching the Ricci component times an expression that relates the acceleration and speed of the universe's expansion. The curvature constant also tracks along, altering the 0 point of such changes to the scale factor. The Ricci scalar across the bottom is exactly the same as before, except now we've kept the c's around. I leave it as a short exercise for the student to show that we could have put the c's in the previous equation after we finished the derivation. Their location makes sense when you take into account the units associated with the expression to the right. So we've gone through this process twice. What are the objects that we've created? The Riemann curvature tensor shows how a vector changes as you move it along a geodesic. The Ricci tensor sums up all those vectors and therefore shows you how the volume of a small region of spacetime changes as you move it along a geodesic. And finally, the Ricci scalar is a coordinate-independent measure of the total curvature of the spacetime. These are the essential tools for measuring the shape of spacetime. We now need a way to link them to the contents of the universe. Before we do that, let's just lock in what metric we're going to use with this textbook and for the rest of the series. This is Rydon's Friedmann-Lemaitre-Robertson-Walker metric form, and the little r is a unitless co-moving radial coordinate. Big R naught, also unitless, is the characteristic coordinate curvature radius. Kappa is the curvature constant with only 3 unique values. A of t is the scale factor, which has units of length. In her textbook, Rydon keeps the factors of c, g, the Boltzmann constant, and h bar, which often in cosmology texts are set to unity to keep things clean, but often obfuscate the physical parameters to people who are just being introduced to this subject. With that out of the way, our final step to encoding the curvature of spacetime into something that we can relate to what lives in spacetime is to define the Einstein tensor. It is the Ricci tensor minus half the metric times the Ricci scalar. Why this exact formula? It has the distinction of being the only combination of the Ricci scalar and tensor where the divergence is 0, which is what we see in the green equation off to the right. This particular property means that we found a conservation law. Conservation laws are incredibly important in physics. Conservation of space-time curvature might sound a bit odd, but if you think about it, it's probably one of the most necessary things out there for our studies. It means we've found something where if we can relate it to its contents, meaning the amount of energy, matter, and momentum in a volume, then we found a way to link stuff to space-time curvature. This is exactly what we need to lock it to gravity. We can see the components of the Einstein tensor for the time-time and space-space components as expressed with Rydon's metric. They arise from the Ricci tensor and scalar you see in the small print. But how does this Einstein tensor then link to gravity? The answer is here, the Einstein field equations. It's not just one equation, but rather there are 16 possible components depending on the metric. In our case, with an isotropic and homogeneous spacetime, there are only 10 independent equations, and with the Friedmann-Lemaitre-Robertson-Walker metric, there are only 4. In yellow, we see the Einstein tensor, which codes all of the spacetime curvature elements. On the right-hand side, we see some constants times the stress energy tensor, T sub mu nu. In between, we have lambda, the cosmological constant times the metric. The stress energy tensor describes the density and flux of energy and momentum in spacetime. It is an extension and generalization of the same set of equations from Newtonian physics. The tensor arises from all the non-gravitational force fields, as well as the matter content and the radiation content, and their motions existing in the spacetime. All this stuff embodies the density and flux of energy and momentum. These are then the sources of the gravitational field. This greatly extends Newtonian gravity's complete reliance only on the mass density as gravity's source. Yep, you heard that right. Not just matter being present in space, but also its momentum, meaning its energy of motion counts too, as do photons and the electromagnetic force. That contributes to the stress energy tensor. Basically, everything counts in the Einstein field equations towards the shape of spacetime, except for zero-point scalar fields that may exist. That's what the cosmological constant lambda is for. It describes some energy density that is constant throughout the space no matter the size of the space. No matter where or when you take that measurement, this constant will be the same. It is a property of the spacetime itself which does contribute to the evolution of spacetime. It was first introduced by Einstein when he wanted to create a static universe, since that was the prevailing thought at the time. Then Hubble found the expansion, and Einstein thought it was a big mistake. Then in 1998, dark energy was discovered, which reintroduced the cosmological constant back onto the scene. We don't have to leave it as a separate component. It can be easily incorporated into the stress energy tensor and called vacuum energy, but it's usually left outside in the form that you see here for aesthetic reasons. So what are the constants in front of the stress energy tensor? They serve as conversion factors between the energy density of the components of the tensor and the odd units of the Einstein tensor and cosmological constant. G is the Newtonian gravitational constant, and c is the speed of light. The 8 pi comes about because of the symmetry of the spacetime. Now, there might be some of you who are saying, hey, wait, where'd the Einstein field equations even come from? Well, you're going to have to look out for my video where I derive them from the Einstein-Hilbert action ansatz. In the meantime, you'll just have to take it as spec that these are the equations we're hunting for. Well, is that fair? Well, this video is already pretty long, and Ryden does the same in her textbook. Well, I'll release that video showing the derivation when I do the upcoming lecture on the Friedmann equations. Well, there you have it, the Friedmann-Lemaitre-Robertson-Walker metric. I extended what was in the textbook to get ready for a true understanding of the Friedmann equations, which give us the evolution of the scale factor through cosmic time. That means we'll soon be able to discuss in detail how the universe expands or may contract as time progresses. I hope you enjoyed this video. If you did, please subscribe, hit that like button, and share it around on social media. I also want to invite you to become a YouTube member. You'll get videos like these earlier than everyone else, plus you'll get little bonuses. Or, if you prefer, please become a Patreon supporter. Both kinds of support go a long way to helping me to get more of these videos out to you. Thanks again for watching, and we'll see you next time.